Okay, so we will study the practice question for chapter 17. So for chapter 17, we have 15 questions on the practice. So the first question is, what is the pH of a solution made by adding 0.30 moles of acetic acid and 0.20 moles of sodium acetate? So sodium acetate is the base. So we know we have a total volume of the buffer is 1.0 liter. For acetic acid, the Ka equals 1.8 times 10 to the negative 5. So again, acetic acid is HC2H3O2. Sodium acetate is NaC2H3O2. Na plus ion is a spectated ion which did not participate in the chemical reaction. Acetate is C2H3. So there's so this will be 3. And O2, which is the conjugate base of HC2H3O2. So we know some of those fundamental definition. Molarity should be moles over liter of solutions. So acid again is HC2H3O2. The angle bracket means molarity. So E equals moles over liter of solutions equals 0.30 molar. Usually when you see the capital M, which means molar. So this base or the weak base is C2H3O2, one negative anion. So that anion's concentration will equals the concentration of NaC2H3O2 because there is one of this base for one of this salt. So we're given this much more of the salt, so therefore we find out this molar concentration, which is the molar concentration for the base. Okay, so once we have those information, one way to solve this problem is using the IC table. The other way is using the Henderson-Hansbach equation. To use the Henderson-Hansbach equation, we need to check this 100 times Ka. 100 times Ka less than C0. So Ka is the weak acid dissociation constant. C0 is the initial concentration of the weak acid or its conjugate base. In this problem, C0 for the weak acid equals 0.30 molar. C0 for the conjugate base acetate equals 0.20 molar. Ka equals 1.8 times 10 to the negative 5. Therefore, 100 times Ka equals 100 times 1.8 times 10 to the negative 5. So that becomes 1.8 times 10 to the negative 3 equals 0.0018, which is less than 0.20 or 0.30. So therefore, we can use the Henderson-Hansbach equation without too much errors. So therefore, we will do both way here. So the first is using the IC table. To use the IC table, we have to know the buffer equilibrium. So the buffer equilibrium is written here in this equation. And then those numbers here, 1, 1, 1, and 1 are the coefficient. So use the IC table, we see our acetic acid is a reactant. Water is not in the table because water's concentration does not change. And then we have this H3O plus aqueous, and we have this acetate aqueous. So we have the initial, I is initial, The initial concentration for the acid 0.30, H3O plus is 0. I write this symbol means approximately 0 because some of those H3 plus, H3O plus come from the water auto ionize. So this is the conjugate base concentration, initial concentration 0.20. Then we decide what are the change. So the reactant change will be negative. So negative how much X depend on the coefficient, negative 1X. For the product, the concentration increases, therefore plus X, plus X. At equilibrium, the concentration equals 0.30 minus X and X, X. So then we plug those values for Ka and the equilibrium expression for the acid, for the H3O plus, for the conjugate base into this equation, and we get this equation here. Because we already know 100 times Ka equals 0.0018, which is less than these two initial concentrations. So therefore, we can use a small x approximation. That is, we will drop x when x is added to 0.20 on the top here, or when x is subtracted from 0.30 at the bottom here. Then the above equation, then this equation becomes this. So then solving this equation for x, we can just say x equals, what we did is multiply this these fractions on the left side of this equation, and also what we did is also write on multiply this fraction on the left side and also multiply this fraction on the right side. So therefore, we can see the result is x equals this number, which 2.7 times 10 to the negative 5. Then we check into the IC table, can see x representing the H3O plus at equilibrium. So therefore, we know H3O plus at equilibrium equals x equals 2.7 times 10 to the negative 5. So therefore, the pH equals negative log of H3O plus molarity equals negative log, and then this number. Okay, so let me correct. There's a error here. So start deleting this equal sign. Okay, so let me do that. Don't need that equal sign. Okay. Okay, so then finally you get the pH 4.57. So the answer is A. Or we can use the other way, using the Henderson-Hasselbalch equation. So using that equation, and we simply plug those numbers in and find out pKa. So we know pKa equals negative log Ka. Using those number and calculator, we find 4.745 for pKa. Then we plug the concentration of the base. So base is C2H3O2. So C2H3 and O2. So equals 0.20 molar, then the acid concentration is 0.30 molar. We put into the equation. So pKa, this number, then basic concentration on the top, acid concentration at the bottom. So we get a 4.57, the same result as we get from the IC table. So the answer is also A. The second question is you want to calculate the number of gram of ammonium chloride. Ammonium chloride formula is NH4Cl, which is our acid, that must be added to 2.0 liter of 0.500 molar ammonia. Ammonia formula is NH3, which is our base. So how much of those acids we need to add into our base solution to make a buffer of pH 8.20? Assuming the volume of the solution does not change as the solid ammonium chloride added, Kb for ammonia is 1.80 times 10 to the negative 5. So as we know in this buffer, the acid is NH4 plus. NH4 plus comes from the ammonium chloride. The base is NH3. The equilibrium for the ionization of the acid is NH4 plus water and has Ka, produce H3O plus NH3. The Kb for the equilibrium should be Kw divided by Kb. Kw is the ion product constant for water at 25 degrees Celsius. We know Kw equals 1.00 times 10 to the negative 14. Kb is the ionization constant for NH3 equals 1.8 10 to the negative 5. So here we should change into negative 5. And so therefore, Ka for NH4 1 plus will equals 10 to the negative 14 divided by 1.8, 10 to the negative 5, equals this 5.5556 times 10 to the negative 10. Okay, so because 100 times Ka equals 5.5556 times 10 to the negative 8, which is less than the initial concentration of NH3, that equals 0.50 molar. Therefore, we can use the Henderson-Hasselbalch equation. So pH equal to pKa plus log base over acid to solve the problem. To first find pKa, just using negative log Ka equals negative log this 5.5556 times 10 to the negative 10 equals 9.255. So the given pH is, or the desired pH equals 8.20, the base concentration 0.50. We plug this number pKa, this pH, this base concentration into our Henderson-Hasselbalch equation. We get this equation. And then we subtract this 9.255 on the left, subtract this 9.255 on the right. So we get this new equation. So this new equation, what we do is take the power of 10 to both sides. So therefore we have power of 10 and so that means you have this side, you take the power of 10, it becomes that. Then this right side power 10 becomes that. So you use calculator, find out 10 to the negative 1.05 equals 0.08810, and then on the right side, 10 and log are anti-log, so they cancel out. So therefore, finally, we get this equation. So that means these two cancel out. On the right side, we simply have 0.5 over acid. We solve this for acid concentration. So acid concentration equals 0.5 divided by 0.08810 equals 567 molar. We needed to know the gram. So therefore, we had to use, we have to know the moles. So right now, this is the molarity. So the given solution is 2.00 liters. So therefore, we use the molarity, capital M, times the volume. We get this much moles of the acid. And more of the acid equals more of the salt. So therefore, equals 11.35 for the salt. Then use the molar mass of NH4Cl, ammonium chloride. We can calculate the gram. So the molar mass of ammonium chloride, simply just see there's one nitrogen, 4 hydrogen, 1 chlorine. So we multiply and add, we have a 53.5 gram per mole. So therefore 11.35 mole times 53.5 gram per mole, we get 607 gram, and the answer is B. So next question is, we have a buffer made by adding 0.40 more acetic acid, has formula HC2H3O2, and 0.40 more sodium acetate, so NaC2H3O2 to enough water to make 1.0 liter of solution. Then you want to calculate the pH after adding 0.010 more of NaOH. For acetic acid, Ka equal 1.8 times 10 to the negative 5. So this diagram below shows a problem when adding strong acid, strong base to a buffer. You're starting from this buffer, you think about in the buffer, you have weak acid and conjugate base. So when you're adding strong acid, you take the conjugate base plus H plus produce the conjugate weak acid, and then you think about when you add in strong base, you will take this weak acid plus hydroxide from the strong base, produce a conjugate weak base plus water. So therefore, you will calculate the new value of the acid and the base. Once you get the new value of the concentration or moles of the acid base, you can use either Henderson-Hansberg equation or IC table to calculate the pH. So these are the two typical stage. First, stoichiometry calculation in this circle here, which depend on what we add. You are using either this equation or this equation to calculating the new value of the acid and the base. Once you get the new value of acid and base, you can calculate the pH by using IC table or the Henderson-Hansberg. Okay, so let's do the step one, stoichiometry calculation, step one here. So remember in a buffer, there's a weak acid and a weak base. When strong acid is added using the weak acid of the, when strong base is added using the weak acid of the buffer to react with the added on strong base. In this problem, the weak acid is acetic acid, the added on strong base is NaOH. So therefore, let's write the equation between this acid, this base. So acid, base, produce conjugate base and water. So the coefficient here is 1 and 1 and 1 and 1. Now make a stoichiometry calculation table similar as the IC table, but this stoichiometry calculation table is for a non-equilibrium reaction, which means goes one way to the right. So carbon of exception, as we said, is 1. After reaction, the moles of the limiting reactant become 0. Second is it is convenient to use moles in a stoichiometry calculation table. So before the reaction window, we have 0.400 moles of the acid. We have added 0.010 moles of the NaOH. We also have 0.400 moles of sodium acetate. So first you find out who is the limiting reactant, so we call that LR for abbreviation. So we know these two reactants are reacting with 1:1 ratio. If they react with 1:1 ratio, it's easier to find the limiting reactant. So the limiting reactant will have the less moles. So NaOH has less mole than this acetic acid. So therefore, NaOH is the limiting reactant. So once we know who is the limiting reactant, then the change will be the initial amount of the limiting reactant. So initially the NaOH has 0.010, then the change will be negative 0.010, because you take these two numbers, add, you get 0. So that's why this is the limiting reactant. So therefore, the change for this one is also negative, and the coefficient is also 1. So therefore, also this 0.010. For this product, the change will be plus, and coefficient is 1 here. So therefore, the number is also 0.010. So then we subtract this number from that, we get 0.390. So for NaOH becomes 0. For this NaC2H3O2 we adding this number to that, we get 0.410. Okay, so this is our acid and this is our base. So once we know the information, the new acid base moles or molarities, then we can use either the Henderson-Hasselbalch or the IC table. So we can see we use here, the first we use the Henderson-Hasselbalch, and to use Henderson-Hasselbalch is very similar as using IC table with the small x approximation. So to use that, you will check this condition. You take 100 times Ka. If you get a number less than C0, so then that means you can use the Henderson-Hasselbalch equation and get the answer correct or accurate. Right. So just one technique, when you use the Henderson-Hasselbalch equation, you can simply use the mole ratio instead of the molarity ratio. So here I show the Y. We know molarity equals mole over volume. So therefore for base will be more of base over volume. And for acid will be more of acid over volume. So therefore, initially the definition in the Henderson-Hasselbalch is a molarity of base over acid of base over molarity of acid. So therefore, we substitute these two expressions into this equation. We get more of base over volume over more of acid over volume. Then we can see the volume cancel out. So therefore, this molarity ratio become more ratio. So then more of acid and then more of base and more of acid. Right, so therefore that will simplify a couple of steps of calculation. So when we use Henderson-Hasselbalch, we don't have to find out the molarities of those base and acid. We can simply use the moles of the base and acid. And from this table, we find out our mole of base is 0.410, mole of acid is 0.390. So therefore, we put into this equation, we get the pH 4.77. So therefore, the answer is D. So the next question is calculating the equivalent point when 25.0 milliliter of 0.100 molar KOH solution is titrated with 0.200 molar HNO3 nitric acid. So to do that, we see our step one is write the balance equation between the acid and the base. So our base is the KOH, our acid is HNO3. That produces KNO3 then H2O. So second step is to calculate the mole of the acid or the base, whoever has both the volume and the concentration given. In this problem, the volume of acid and the concentration of the acid are given. So let's find out the moles of the base. So we will use the volume of the base and then the concentration of the base. So before we use the concentration of the base, we have to convert the milliliter of the given volume into liters. Then we take the concentration of the base, then we find out more of the base. So next step is using the coefficient ratio, convert the mole of the base into mole of the acid. So we find out from step 2, we have this much more of the base. The mole ratio between the acid and base is 1:1 from this equation. So therefore, we have a 0.00250 mole of the acid. So next, using the moles of HNO3 from step 3 and the given concentration of HNO3 to find volume of HNO3. So we start with this much more of HNO3, and this fraction is coming from the concentration. You can see the concentration more cancel out, get a liter. So we want to see the milliliter, so therefore we use the last fraction, 1 liter equals 1,000 milliliter. So we have 12.5 milliliter of HNO3. So therefore the equivalent volume is 12.5 milliliter of HNO3, and the answer is C. Okay, so question 5 is when 25.0 milliliter of 0.100 molar KOH solution is titrated with 0.200 molar HNO3, calculate the pH when 10.0 milliliter of 0.200 molar HNO3 has been added to the initial 25.0 milliliter of 0.100 molar KOH. So this is the strong base, strong acid titration. So to find out the pH, we will follow these few steps. So step 1 is write the balance equation between the acid and base. So base acid 1:1 ratio. So then you calculate the moles of the acid and the base. We have 25 milliliter of the base KOH. Using this fraction, converting from milliliter to liters, and using this molarity to get moles of the base. Do the similar conversion for the acid. We have 10.0 milliliter of the acid, and 1 liter is 1,000 milliliter. We have this molarity for the acid. We have this much more of the acid. Then we can use this type of table to find out the limiting reactant and calculate the leftover of the excess reactant. If the reaction has one ratio between the two reactants, and the limiting reactant is the reactant that has less moles, so this has less mole compared with this number. So therefore, the change for the limiting reactant will be the negative of the initial moles. So therefore, the change for this also the same number because they have 1:1 ratio. So therefore, the product will increases even though this product does not matter. So I copy that wrong. So this will be the K. And but just for completing the problem, we also want to see what is the change for the product. Water doesn't matter because we have water, plenty of water. What is the solvent? So we know the initial concentration, initial moles. We know how much more they change. We put them together, so the mole after reaction for the acid becomes 0. That's why the limiting reactant. And for the base, we subtraction, we have this much more of the base excess or leftover. For the product, we have that, but this product is pH neutral, so therefore does not matter for our calculation for the pH. So this product KOH is pH. So KNO3 is a pH neutral. So it's pH neutral, so we don't have to worry about that. We just find out the molarity of the excess base. The excess reactant or the excess base is the KOH. So we have this much more of KOH not used. And obviously there's a strong base will control the pH of our solution. And the total volume so far we have 25 more of the 25 milliliter of the base, and we have 10 milliliter of the acid, so altogether we have 35.0 milliliter. We're converting milliliter into liters by using this equation. So here we forget to change, so this will be the liters. And So therefore, the molarity of QH equals more of QH not used divided by liter of the total solution. So not used more of QH is 0.00050 divided by liter of solution 0.0350. So we find this much molarity of QH. So in one QH, there is only one OH. So therefore, this hydroxide concentration also 0.0143 molar. Then next, we'll take the negative log of the concentration of the hydroxide, get the pH. So pH is 1.845. So then 14 minus pH, 14 minus 1.845. So 12.155 is the pH. So therefore, the answer is A. Okay, question number 6. I think we still have the same titration. So we have 25.0 milliliter of 0.100 molar QH solution. It's titrated with 0.200 molar HNO3, and you want to calculate. So the pH when 15.0 milliliter of 0.200 molar HNO3 has been added to the initial 25.0 milliliter of 0.100 molar QH solution. So the step is similar. We want to write the equation between the acid base. So the base QH and acid HNO3 produce KNO3 then water. So then we calculate the moles of the acid base. So we use our volume of the base 25, converting 25 milliliter into liter using this fraction, then using this molarity fraction, get the moles of the base. Do the similar conversion for the acid. So first milliliter into liter by using this fraction, then liter into moles by using the second fraction. So we have this much moles of our acid. Then we were using the table, so we tabulize the information. We have initial moles of the acid, initial mole of the base. Then we can see who is the limiting reactant. So again, if the reacting with one ratio between the base and acid, so whoever has less mole will be the limiting reactant. So this mole 0.0025 is less than 0.00300. So therefore, the KOH is the limiting reactant, and the change will be the initial moles of the limiting reactant. So therefore, negative 0.0025 is the change for KOH. 1-to-1 ratio, so therefore the change for the other reactant is also negative 0.00250. For the products, again, does not matter because the product is pH neutral. So therefore, so there's a typo here. So just for completion of the problem, so we want to see how much of the product produced. All right. So therefore, we have this mole of the acid after the reaction, which is the excess or leftover. We have this much more of the salt produced, which is the pH neutral. And LR is for limiting reactant. So LR is a QH, becomes 0. So next, you just find out the molarity. So molarity is mole over liters. So far, we have our total volume. So volume of the base plus volume of the acid is 25 plus 15 is 40 milliliter. We're converting 40 milliliter into liters. We get 0.0400 liters. And so therefore, the leftover molarity of the acid will be the mole of the acid not used divided by the liter of the solution. So mole of acid not used is 0.00550 divided by the total volume, which is 0.0400. To get this much molarity, 0.0125 molarity of HNO3. So HNO3 is the monoprotic acid, the strong acid. So one HNO3 will give us one H plus. So therefore, it will give us 100% of H plus because it's strong acid. So therefore, we also have 0.0125 molar of H plus. Once we know the H plus molarity, we take a negative log, we get a pH 1.903. So the answer is E. Next question is titrate 40.0 milliliter of 0.0350 molar benzoic acid. So benzoic acid is a weak acid, so therefore our problem changed a little bit. So this is a weak acid. And then we use our base. So this NaOH is a strong base. Okay, so therefore our titration problem become a weak acid with a strong base. So strong base weak acid titration. And so this question is calculating the pH of the solution before addition of any NaOH. So before addition of any strong base, to find the pH of the weak acid solution, you just use like what we did in chapter 16. For example, in practice question number 8, just write the weak acid ionization equilibrium. So we have this equation here. Then you write the equilibrium constant expression, so Ka product over reactant. Then you set up the IC table. So initial concentration of the weak acid 0.0350. So this H3O plus approximately 0, then this conjugate base benzoate 8 is 0. Then the change, so we're shifting the equilibrium from left to right. Therefore, this is negative x, and the plus x, they are always they are in this way because the coefficient here is 1 and 1. So therefore, at equilibrium, 0.0350 minus x and x and x. So next, we'll take these three, this number here, this expression here, this expression here, this expression, and substitute them into that equation. So therefore, together with the given Ka, we have this equation. So one assumption we can make is drop x when x is subtracted or add to a number. In this problem, we can drop the x in this expression because compare x with 0.035, x is much small, negligible. Therefore, 0.0350 minus x equals 0.0350. So this assumption is called the small x approximation. It is valid if 100 times Ka less than the initial concentration of the weak acid. So let's check it. And we can see our Ka is 6.3 times 10 to the negative 5. So therefore, 100 times Ka equals 100 times 6.3 times 10 to the negative 5. That equals 0.0063, which is less than 0.035. So therefore, we can use this approximation. So we can use this approximation. Let me change that. All right, so therefore this equation, initial equation, become simplified. We can see the difference here. There's minus x here, so there's disappeared. We dropped that. So to solve this equation, which is simple, so if you rewrite this equation, so that become this, and so x times x squared, and this denominator is 0.035. You multiply this on both sides, then take the square root, you get this number here. So then you go back to the IC table, you will see X is the concentration of H3O plus at equilibrium. So H3O plus is the same as H plus. So once you get H plus concentration, you take negative log, so therefore you get a pH. And the answer is E. So the next question is question number 8. So you titrate the same titration, but this time you want to calculate the pH after adding some of those strong base. So after adding 18 milliliters, 18 mLs. Right. Similar approach as the titration of strong acid, strong base. So you write the equation between the acid base. So the base is NaOH, the acid is C6H5COOH. So they produce the conjugate base and water. Then we calculate the mole of the acid. We know the volume of the acid, and we convert in milliliter into liters. And then from liter to mole, we get this much mole of our weak acid. We do the same calculation for our base. So we have 18 milliliter of the base converting to liters and using molarity of the base, get more of the base. Then we summarize those information in this table. So we have our acid base, then our conjugate base. So there should be an Na. So we decide the limiting reactants. So as we said before, if the reactant reaction in the reaction is 1:1 ratio, so the one has less mole will be the limiting reactant. So NaOH is the less mole, so therefore NaOH is the limiting reactant. So then the change will be the negative of the initial moles of the limiting reactant. So therefore, the change for NaOH will be negative 0.00126. So therefore, in that way, you take the initial and the change and sum them together, you get 0. So therefore, this is the limiting reactant. And then how much change for the other reactant, which is our weak acid, because the 1:1 ratio, so therefore the same number and the same sign. You take the initial, then you take the change, you get this much of leftover acid, weak acid. Then this conjugate base, the change is plus. Then the number also the same number because the coefficient also 1. So therefore, you take the initial 0 plus the change, you get this much base produced. So that you know the total volume is the volume of the acid plus volume of the base. So therefore, we have 58 ml. So that becomes 0.0580 liter. So therefore, the molarity of the leftover weak acid will be the leftover moles divided by the total volume equals 0.00241 molar. Then the conjugate base, the produced conjugate base molarity. So this is really the base, this is the salt. So we know this salt moles produce this much. So they are 1:1 ratios. Therefore, we find out this conjugate base molarity by using the moles of the salt divided by the volume, get this molarity of the base. So then the next step is using the IC table of the Henderson-Hanselbach. So from step 3, we can see that we have a buffer. We have a buffer in the solution after null because we have a weak acid. We have also produced conjugate weak base. So the pH can be found using the Henderson-Hanselbach equation because 100 times Ka is less than the initial concentration of this. But it's larger than that. I use IC table using the quadratic formula without the small x approximation. I get H plus is 5.157, so this kind of accurate result. So if I use the Henderson-Hanselbach equation, so I plug those numbers, the molarities of the base and acid, and get a pKa by using the Ka. So this is Ka for the benzoic acid. I get a 5.155. So the answer is 5.155 because so the answer A is 5.155 because as I said, for our class, when we have a problem of find out a pH for a buffer, we can just use Henderson-Hanselbach. Okay, so number 9 question still have the same titration. but you want to find the pH of the solution at the equivalent point. So we will follow the similar step as in question 8. We first write the balance equation between the base and acid. Then we calculate the moles of the acid, because acid has the same has the concentration given and also the volume given. So then we use the coefficient ratio from the balance equation in step 1, find out the mole of the NaOH using this conversion here. Then once we know the mole of NaOH, we use the molarity and then use the equation between liter and milliliter. We find the equivalent volume is 20.0 milliliter. Okay, so therefore we were using this table to see what we have are at the equivalent point. So at the equivalent point, we have the same mole of the H plus, same mole of hydroxide, and they both 0.00140. We don't have the base produced yet before the reaction. So after reaction, we'll produce some of those conjugate base. And how much we produce depends on the limiting reactant. And in this case, both of them are limiting reactant. So therefore, we have this change for the two reactant. We have this change for the products. Then we have zero left over for the acid, zero left over for the strong base. We produce this much more of the conjugate base. So we want to find out the next step. We want to find out the total volume in the solution now. So we have 40 ml of the acid. We have 20 ml of the strong base. We altogether have 60.0 ml. So that equals 0.0600 liters. Then we can see from this formula. So this is the salt and this is our conjugate base. We have a 1-to-1 ratio. So therefore, more of the salt divided by liter solution equals molarity of the salt, which also equals molarity of this base. So next step, we'll use the IC table to solve in a weak base problem, because you can see after reaction, we don't have acid anymore, we don't have the strong base anymore, we just have this conjugate base. So therefore, you write out the equation between the weak base and water. So the weak base is this benzoate, then water, then produce hydroxide, produce conjugate weak acid. So this equation has an equilibrium constant, and this equilibrium constant we will call that Kb. So therefore, to find Kb, you are using the equation like here. So Kb equals Kw divided by Ka. So now we know Ka is given for the benzoic acid, and Kw is a constant. So you put this number here for Kw, you put this number here for Ka. So we get this equation, or get this fraction. Therefore, we find Kb for this equilibrium is 1.59 10 to the negative 10. And so therefore, the IC table becomes this. Initial concentration for the weak base, we find from this number here. Then the initial hydroxide approximately 0, because some of the water produces a smaller amount of hydroxide, but negligible. So it's therefore approximately 0. This weak acid is 0, then the change for the reactant is negative x for these two products plus x. So put together the initial change, we get the base equilibrium expression is 0.0233 minus x. Then the concentration of hydroxide is X. The concentration of the acid is X. So next, we will write the equation for the Kb, and then we plug those numbers X for the two products, 0.0233 minus X for the reactant into this equation. Then we can use a small x approximation because this Kb is so small. So that means 0.0233 minus x equals 0.0233. So therefore, this equation becomes simpler to solve. So therefore, we can see how that becomes that. Basically, if we use this approximation, that equation become 1.59 times 10 to the negative 10 equals x squared over 0.0233. Okay, so this is after we use the small x approximation. So next step, you want to find the x, so you will times this 0.0233 here. Then you also times or multiply 0.0233 on the left. So here I cancel out, and then you take the square root of the left side, take the square root of the right side. So therefore you have this equation here. And then you check back into the ICU table, and you can see what is x. So x is here. That means it's for the hydroxide. For the hydroxide at equilibrium. So therefore, we find out hydroxide molarity equal to x equals to 1.925 times 10 to negative 6. And we take the negative log of hydroxide molarity, we get a pH. So therefore, we have 5.716. The problem is to find the pH. So therefore, pH is equal 14 minus pH equals 14 minus 5.716 equal 8.284. And the answer is B. So the next question is same titration, but this titration is we have add a little more of the base. So we have adding 25 ml. The process is we follow the similar process, but we realize our equivalent point for this titration is 20 ml NaOH. So therefore, after adding 25, so that's it beyond or after the equivalent point. So what we do, follow a similar process as what we did in question number 8. So we will write the equation between the base and acid, produce a conjugate base. Then we calculate more of the acid, more of the base. So more of the acid. We're starting with the volume in ml of the acid, converting into L, then use the molarity, get more of the acid. Then we see the volume of the base, converting from ml to L. So then we use molarity of the base, get more of the base. Then we summarize the information in this before change after table. So before reaction, we have this much more of the acid, we have this much more of the base, we have 0 more of the conjugate base. Then we have change. We find our limited reactant because we one ratio between the two reactants. So the less more reactant is the limited reactant. The change will be the initial amount of the limited reactant. So initial mole of the limited reactant is 0.00140. So therefore the change is negative 0.00140. The same change for the other reactant because they have 1-to-1 ratio. All right. So therefore, the same negative 0.00140, then the change for the product is also 1-to-1 ratio, but the plus sign. So therefore, after we adding the initial with change, we have 0 for the limited reactant, and for the excess reactant, we have this much left over. And we also produce this conjugate base. So there are 0.00140 moles of the conjugate produced, but this is the weak base. Because NaOH is a strong base, so the leftover NaOH will dominate the pH of the solution. To calculate the leftover NaOH molarity, we follow this process. We first find the total volume of the solution, where 40 plus 25 equals 65, that much liters. And then we take the leftover moles divided by the total volume in liters, we get this much molarity of NaOH. So we know NaOH gives us 1 OH, so therefore OH, the hydroxide molarity equals NaOH molarity equals 0.05385 molar. So pOH equals negative log of OH equals 2.269, then pH is 14 minus pOH equal 11.731. So therefore the answer is D. All right, so question 11 is about which of the expression here is the solubility product constant, KSP, for this PbCl2 in water. So to do that, you first write the equation for the solubility equation for this given salt. So the given salt is PbCl2 solid. So solubility equilibrium where we simply take this one of the salt and separate them into ions. So you have to remember what ion in the salt. So when you say Pb, maybe Pb2 plus or 4 plus, depend on the formula. So here the Cl2, which means we have 2 Cl, 1 negative. So therefore the Pb is 2 plus. So once you get this equation, you can see these two coefficients come from the subscript 2 in the initial formula for the salt. So once you have the equilibrium equation, then you can write the KSP. Typical as the KEQ for the equilibrium, you write the product on the top, reactant at the bottom, but you don't see the reactant at the bottom because the reactant is solid. So solid, which means the concentration does not change. So solid or liquid, they will not show in the equation for the K, whether your K is KSP or Ka or Kb. So that's why we have the reactant, but this reactant is in a solid state, so therefore it not show up in the KSP. So then, therefore, the answer is E. Just be careful with those notation here. This one is subscript. Here the superscript. The superscript means exponent. That's the right answer. So this subscript just not the right answer. Okay, so the next question is 12. So give you the KSP for CaF2 calcium fluoride is 4.910 to the negative 11 at 25 degrees Celsius, asking for the molar solubility. So molar solubility means how much molar of this given salt dissolve in water. So to solve this problem, you write up the solubility equilibrium. You take one salt, 1 unit of the salt, which is CaF2 solid, then separate them into ions. You have Ca2 plus ion, and 2 F1 negative ion. So again, where the 2 come from? The 2 come from this subscript. So the coefficient 2 come from the subscript 2. So therefore, we know how much ion we produce. Then you write the equilibrium constant. We call that a KSP. So KSP equals Ca2 plus F1 negative squared. Then we write the IC table. So again, solubility referring how many molar of this salt dissolve. So if you have X amount of this salt dissolve, then from this equation, you can say if this X amount, X molar dissolve, then you will see the 1-to-1 ratio for this guy. So therefore, you will have a plus X for the Ca2 plus, but you have plus 2X for the F1 negative. So therefore, once you know the initial and the change, you sum them together, you get the equilibrium. So next, you plug this number into this equation, and also plug the KSP into this equation, you get this equation. So this equation, if you see how you get this result, you can think about take the right side of this equation, which is x times 2x squared. So 2x squared, that means you square the 2, you square the x. So therefore, you get x times 4 times x squared. That becomes 4x to the cubic. So 4x to the cubic equals to that. Then you divide 4, then you take the cubic root. So therefore, you get this number here. So now you find out the X. So as we said, X is this molar solubility for the product. So therefore, we find our answer is X. So therefore, it's 2.31 times 10 to the negative 4. The answer is C. So next question is you add 10.0 gram of solid carbon 2 phosphate. Formula for carbon 2 phosphate is CO3 Pu42. Okay, so you get that one by review what we learned in Chem 113. So carbon 2, which means you have carbon 2 plus ion, and phosphate is Pu43 negative ion. So you switch the charge, you get this formula. So you're adding this salt to a beaker, then you're adding 100 milliliter of water to the beaker at a temperature 298 Kelvin. The solid does not appear to dissolve. You wait a long time. With occasionally stirring, then eventually with some solid carbon 2 sulfate left over, at the bottom of the beaker, you measure the equilibrium concentration of the CO2 plus ion in the water. You get this much CO2 plus ion. So that means even though there are still some solid left over, there's a small amount of this salt dissolved in water. So therefore, you have a saturated solution. So therefore, you want to calculate what is your KSP. You just using this equation. So you see the equation for the solubility of carbon 2 phosphate. We take 1 of this salt unit, produce 3. So the 3 coming from subscript. We produce 3. Sorry, that should be Cu, not Ca. And then we produce also the phosphate. So the phosphate is Pu43 negative. So how many phosphate produce also from the subscript of the phosphate. So the subscript for the phosphate is 2, so therefore the coefficient is 2. Then we write the equation for the KSP. So we have 2 products in aqueous. So CO2 plus in aqueous, so therefore in the equation. Then what is the exponent? So the exponent will be the coefficient. Okay, so therefore we have this coefficient here. So we have this coefficient become exponent. And similarly for the other product. So where is this reactant? Well, not in the equation because this reactant is solid. Okay, so next we'll use IC table. So this solid down note appears in this IC table because solid concentration is constant. So therefore, we have initial 0, we have plus 3x, plus 2x, then we have 3x, 2x at equilibrium. So then we have another information. We know at equilibrium, the concentration for the CU, as a typo here for the CU, is given. So therefore, we can use that information. So we know at equilibrium for the CO2 plus is 3x. Then the given concentration at equilibrium for the CO2 plus is this number. So therefore, we can say 3x equals 7.01 times 10 to the negative 8. So therefore, we have this equation here. Okay, so once we have this equation, we can solve for x. So x will equals 7.01 times 10 to the negative 8 divided by 3. So that becomes 2.337 times 10 to the negative 8. And then from this here, we see 2x is the concentration for phosphate at equilibrium. So therefore, so phosphate molarity at equilibrium equal to 2x equal to 2 times the x, this number here, then we get this. So now we know the concentration of the phosphate, concentration of the CO2 plus at equilibrium. So next, you just plug these two numbers into the equation for the KSP. So therefore, you will use 7.01 times 10 to the negative 8 for the Cu2 plus ion and raised to the power 3. 4.673 times 10 to the negative 8 square. Then you get this KSP. So the answer is D. All right, so question 14 is asking which of the following salt is more soluble in acidic solution than in basic solution. So basically, for our class, we were just using a simple rule. So if the anion in the salt is basic, then the salt is more soluble in acidic solution. All right, so let's say our first salt is iron 2 hydroxide. So that has the anion hydroxide. So obviously hydroxide is basic. So therefore, the iron 2 hydroxide is more soluble in acidic solution. So to understand why that, we can use this approach. We write the solubility equation for the given salt. So the given salt is FeOH2 that produce Fe2 plus and 2 hydroxide. And then you write the basic anion reacting with acid. Our basic anion is hydroxide. Because we have 2 hydroxide here, so we'll take 2 hydroxide plus 2H plus produce 2 water. So once you have these two equations, you adding them together. So adding this equation 1 with equation 2, you cancel out the hydroxide with hydroxide, you get this overall equation. So in the overall equation, we can say H plus is the reactant. So therefore, using the Li-Hsia-Lai principle, when you're adding reactant, you are shifting, you're adding the aqueous reactant, you are shifting this equilibrium from left to right. So that means you use the solid salt, which means the solid salt dissolve. So that's why for those kind of salt that has the anion that is basic, so therefore they are more soluble in acidic solution. So our second salt is Na2CO3. That's also more soluble in acidic solution because our anion in this salt is carbonate, and carbonate is basic. So to understand that, why they are more soluble in acidic solution, you can also use the same approach as in the last problem. We write the solubility equation for our salt. Then we use this anion carbonate reacting with the acid, produce H2O and CO2. Adding equation 1 with equation 2, we get an overall equation. And from the overall equation, we can see the H plus is reactant in aqueous state. So therefore, adding the reactant, we're shifting this equilibrium from left to right, which means consuming the solid Na2CO3. So the next question is this salt, BAS, is this more soluble in acidic solution? Yes, because our anion or the negative ion is S2 negative sulfide. So to explain this, you can take this salt solubility equilibrium, then the reaction between the negative ion with acid. So therefore, we have these two equations. Then in these two equations, you add, so the S2 negative cancel out, so we get this overall equation. Then in this overall equation, we can see this H plus, which is our acid, exists as aqueous as reactant. So as we said before, Li-Hia-Lai principle will tell us if we add in reactant in aqueous state, that will shifting the equilibrium from left to right, which means use those solids. That means the solid will dissolve more. So the last salt is AgBr is not more soluble in acidic solution because the anion is Br1 negative. So that is not a basic anion, and also the Ag1 plus also not react with H plus. So really, they are not very active with the acids. Therefore, the answer is this answer is not more soluble in acidic. And you check all the others. So 1, 2, 3 salt is more soluble in acidic solution. So therefore, the answer is B. Okay, so the last question is you have a solution has this much molar of magnesium 2 plus ion in your solution. Now ask what is the concentration of hydroxide is necessary to begin the precipitation of the cation. So give you the KSP for the magnesium hydroxide is 1.8 times 10 to the negative 11. So you write the equilibrium equation for the magnesium hydroxide. So these two here subscript become the coefficient here. All right. So we can see for this equilibrium or for any equilibrium, we also have a reaction quotient. So reaction quotient have a similar expression or equation as the K, except when you have the equation for Q, so the Q have those concentrations, and those concentrations can be at any stage. When you have an equation for the K, Ka, Kb, or Ksp, now you know the concentration for those reactant product must be at equilibrium. Then we also learn from chapter 15, when you compare Q with K, so when Q equal to K, that means our reaction is at equilibrium. When Q is smaller than K, our reaction should shifting to the right. When Q larger than K, our reaction was shifting to the left. So for our problem, our left side is solid, So therefore, to produce solid or to produce precipitate, we need this inequality, which means we need Q larger than K, or at least equal to K, have the equilibrium. Then a little more than the K, then you will have the precipitate. So what we will do is we were using this inequality to solve the problem. So we have our Q, which has the expression like here. So we plug the number for Mg2 plus here, and then we don't know the hydroxide concentration yet, so we keep in this equation. Then we plug the KSP. So KSP is given in the problem. So once we have this inequality, and then we divide this number out, and then we take the square root. So therefore, we get the hydroxide concentration is 1.8 times 10 to the negative 5. So that means, so to begin the precipitate, we need this much of hydroxide. So the answer is C. Okay, so that's it for the practice question for this chapter. So for this chapter 17.